Hello, we're going to look at 1.5, and that's mathematical induction. And you can see I have a little, clip art, piece of art here that illustrates, a little comic that illustrates, the logic behind mathematical induction. Now, mathematical induction is a way to prove something to be true. And a way that we logically do that is, first off, we have a set of dominoes here set up, and we have, if we knock over the first block, then it knocks over second, third, fourth, fifth. Just kind of like a sequence. We get the first one, and then we can get to after we have the first term in a sequence, we get the second, a third, all the way to infinity. Before we had formulas, but we didn't actually prove them. So mathematical induction proves them, and the logic behind it is if you know the first block to be true, and then you need to show that every other block after that always works forever. And that's what mathematical induction does. So here is the steps for mathematical induction. So it says we start with a statement, piece of n, which we want to prove to be true for all values of n in the element of the positive integers. First step says prove that the statement is true for the starting value piece of 1. Now that it's important to look over here. They have to the right piece of 1, or n equals 1 in that situation. The starting value isn't always 1, and we'll see some problems like that in the future where you can start off. It just has to be the starting value, whatever it is. Step 2 is assume that your statement, your original statement for k is true, where k has a particular value of n equals n greater than or equal to 1. And that's all you need to do, just assume it to be true. But then step 3 is use the assumption that piece of k is true to show that piece of k plus 1 is also true. And the reason that this proves it is if you assume this guy to be true, and then you find out that this guy plus another one is also true, then the original assumption had to be correct. Otherwise, you wouldn't be able to show that if it was true if it wasn't. So that's the logic behind it. So that's what mathematical induction is. So let's go ahead and let's see an example. Now, mathematical induction is very formal. You must write out everything there is. There's no skipping steps. It's a proof, and you have to show all 3 steps. Then the first step, we label it as piece of 1. Right? Doesn't mean function we're plugging in 1 or anything like that. In that sense, it's just saying that's the piece of set. We're trying to find out for the starting value if the starting value is indeed correct. So the way we do that for this expression, it says use mathematical induction to show that the sum of the first n terms of arithmetic sequence with the first term use of 1 and the common difference d is given by this formula that we've seen before. Now we're going to actually prove that this is using induction, that this actually works forever, right? So the first value is 1 for n equals 1 in the sequence. And then it's 2 times use of 1. If I put 1 in here, this becomes 0. This becomes 0, and 0 times d is 0, so that just cancels out. And then half of 2 is just this. So what did this just show? Well, I know that s of n is equal to first of 1, use of 1, use of 2, plus use of 3, plus dot, 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 all the way up to the use of n term. I found out that this sum right here will give me just my first term in a sequence, and that's what I want, right? So I could say, so piece of 1 is true. Good, and you need to write that piece of 1. You've shown it, then you can say piece of 1 is true. Next step is piece of k, and for piece of k, I want to assume that s of k for k over 2, basically it's going to plug the k into this value, 2 use of 1 plus k minus 1d is true. And that's it. That's all I need to do for the first 2 steps. The first 2 steps are definitely the easiest. It's just setting the groundwork for the proof. I've showed it works for the first step. I know piece of 1 is true. The starting value is true. Then I assume that it's true for some other value k. And I did forget one thing. K is in the element of the positive integers too, and that's very important. You have to give restrictions on our variables if there are any. So, and k could be any positive integer, so I have to write that. Now, first two steps are pretty easy, but I have to, the next step, I want to make sure it works for every other step after k, right? But I want to use my assumption. So what I want to do is show that s of k plus 1 is equal to, what would happen if I put k plus 1? I would end up just plugging it in. It has to equal something like this. 2 use of 1. And then if I put k plus 1 into our original formula, I'm just going to have k times d, right? And that's what I end up, right? Now I want to show that s of k plus 1 equals this to the right. Now, a common mistake is students will work on the right-hand side, and you don't want to do that. I only write this to know what it has to look like. It helps me out with this. You don't even have to write this originally, but I do need to show this. So I want to always work with the left-hand side and move to the right. I write this out, so now I know what it kind of looks like, and I can use it. So what does, I have to start on the left-hand side. So what does s of k plus 1, what does that equal to? If I were to sum this up, I would have the first term plus the second term plus the third term plus. I'd all go up to the kth term, but then I'm going not the k, but the k plus 1. There would be an extra term in here, right? Now, let's look what we have right here. I know that this guy right here is our assumption. This right here is s of k. So I can go ahead and substitute it in. And you always want to look for that. Once you set up your s of k plus 1 appropriately, then you want to know, or your piece of k plus 1 is, you want to find a way to use your assumption. So now I know that I have my assumption, which is k over 2, 2 use of 1 plus k minus 1 times d, plus the next term in the sequence. Right? Well, what is this guy equal to? Well, if we were to figure out what this is a arithmetic sequence, that would be the first term times n minus 1 times d. But if I do use of k plus 1 like I have here, it's going to be the first term plus k times d, because k plus 1 minus 1 is just k times d. So that's what that equals to. So this guy is going to be equal to use of 1 plus k times d. Good. Now I have it set up. I just need to do algebra and make it look like this. So moving on. What do I have? Well, I kind of use this to look. I see I have a 2 here. I have a 2 outside here. The parentheses are here, so I need another 2 here. So I'm going to find a common denominator over here. That way I can take out a half outside of it. And then I'm going to be left with, I'll distribute 2 times k times u1, and then I'll have plus k squared minus k, and then I still have a d, and then I'll have plus 2 use of 1 plus 2kd, and that's what I have so far. Good. Now, I do notice that I have a 2 use of 1 that I can take out here. So I got 1 half, 2 use of 1, and what does that leave me? K plus 1. So that's nice. I know I want to be able to get a k plus 1 out, but I got to be able to get it out of everything over here. And then, let's see. So those two were combined here. Here I can take out a k and a d, right? So I can take out k times d. What does that leave me with inside of here? I'd be k minus 1, right? K minus 1 plus 2, right? That's what I'd end up with, right? Which is k plus 1, right? So this guy right here actually is k plus 1, right? Right there. And then now I have k plus 1s in both of them, and I can factor them out. And then what am I left with? If I take the k plus 1, I can just write it up top. I have k plus 1 over 2. And then if I take out the k plus 1 and the k plus 1, what am I left with? 2 use of 1 plus k times d, right? And there you go. I've used algebra, and I've shown that these two are equivalent. So now I have to finish up the proof, put it all together, I have to write a statement. So now I've done all the steps of induction, I've shown it, and now I have to give my statement putting it all together. And this little symbol here means therefore. Therefore, if piece of 1 is true and piece of k is true, implies that piece of k plus 1 is true, then the statement is true for all n in the element of the positive integers. And there you go. Now, I know it's a lot of work and a lot of writing that you have to do for this, but you can't leave anything out, except for a few things that I've added here. You need to, it's a proof, so you need to formally write out piece of 1, show the first step, tell me that it's true, assume that it's true, make sure you don't forget your restrictions, right? Then you set up your k plus 1, making sure to go left hand side to right hand side, not vice versa. Remember, I set this up just solely so I know what I need to work towards. Then I set up my k plus 1 expression, look for something to substitute in, and then I had to also evaluate this. Then it was all algebra, and I looked at this to try to get there. And then finally, once I've shown what I needed to show, and I have to give my statement as such. And this pretty much is the same either way. And then at the end, you can give yourself a QED. Go ahead, look up what that means. But it's a common thing that mathematicians put when they approve something. Sound good? Thanks.